Hello everyone, in this video I would like to go over the written homework 2.7 on Math 148. Number 3, so the first question is number 3. So from in problem 3 to 8, found all the critical points and local maximum and minimum of each function. So we are trying to find the local maximum, local minimum, and the critical points. So the question is f(x) equals to x squared plus 8x plus 7. Now, first of all, how do we find critical point with derivative? So we know that in order to find critical point, we want the critical point occurs, I should say that the critical point occurs when f prime of x equals to 0. So the first thing we want to do is find the first derivative of the function. So I have f prime of x equals to 2x plus 8. And then we set the f prime of x equals to 0. Then we solve it. We have a 2x plus 8 equals to 0. So x equals to -4 is our critical point. So we need to find the critical point. So we got f prime of -4. We plugged it in. Oh, sorry, we need to plug in the original function. So we have f of 4 equals to f of -4, into the original function to find the y coordinate. So I got -4 squared plus 8 times -4 plus 7. So this is equals to 16, because negative gives you a positive number, minus 13.2 at 7 equals to -9. Then our critical point is when x equals to -4, y equals to -9. So in here, we need to be careful when we're plugging in the number, we need to plug into the original function instead of the first derivative function. If you plug in the -4 into the derivative function, it will give you back to 0, because the first derivative means the slope at that point. Now, we still need to determine if this is a maximum or minimum. So how do we do it? Well, we know that for the second derivative, f of double prime, if is concave up, we have a minimum. If it's concave down, we got maximum. So if it's concave up, our second derivative will be greater than 0. If it's concave down, will be less than 0. So now let's test these critical points if it's a minimum or maximum. So I have a double prime of x equals to, we take the first derivative and a derivative. So remember, our first derivative is 2x plus a. We want to take the derivative of the first derivative. So that I got 2. So that means the second derivative is always greater than 0. So we know that this is going to be a concave up at x equals to -4. So that means if it's concave up, it looks like a bowl, look like a U. That means we have a minimum. So that means at critical point, -4, -9, we got a minimum. Okay, so the second problem I want to go over with is number 6, also finding the critical point, maximum or minimum. The second equation is fx equals to x minus 1 squared and then x minus 3. So we use the same idea. We need to use first derivative and then second derivative. Let's do all the derivative first. Okay, first derivative, as you can see here, has a multiplication. That means we need to use a product rule. A quick reminder, product rule is f of x equals to g of x, h of x. So product rule says that if you take a derivative of two functions multiplied together is equal to the first derivative of the first function times the second function, add the first function times the derivative of the second function. So we're going to do that. So the first function with x minus 1 squared derivative, and then x minus 3 plus x minus 1 squared times x minus 3 derivative. Now, the first function, when we take in the derivative, you might notice that we need to apply the chain rule for this guy. So chain rule states what? So do a very quick review. Chain rule says f of g of x. If we want to take derivative of that, we need to take the derivative of fx, then times g prime of x. So in here, we will have the derivative of fx, and when we look at the whole parentheses as a whole, then we have 2 times of x minus 1 and take derivative of whatever inside the parentheses. In this case, we have the derivative of just x. In our case, the derivative of just x is equal to 1. So that's chain rule. And then times x minus 3 at x minus 1 squared, x minus 3 derivative is equal to 1. Okay, now simplify it. So we got 2x squared. Let me show all the steps. So I have it 2 times x minus 1, x minus 3, plus x minus 1 squared. Simplify it, break it down. So I have 2x minus 2 times x minus 3 at x minus 1. FOIL, I have a 2x squared minus 6x minus 2x plus 6 at, this is the perfect square formula. If you don't remember, here is the quick review. I got a minus b squared is equals to a squared minus 2ab plus b squared. When you're doing that, I would like you to put a parentheses. Right now it's an addition. It won't change the sign. But if it's a subtraction, it will change your sign. So I would like you to put the, when you expand the perfect square, I would like you to put a parentheses here. So I got x squared minus 2x plus 1. Now, merge all the like terms together. I will have 3x squared minus 10x plus 7. So that's the first derivative of the function. Now, we can just find the second derivative in here. In here, second derivative of the function. That means we need to take derivative of the first derivative. So I have 6x minus 10. All right. So now the next step is we need to find all the critical point and see where does the critical point occurs. Now, that means I want to let the first derivative equal to 0. In that case, I have 3x squared minus 10x plus 7 equals to 0. So to solve it, you can either try to factor it or use quadratic formula to solve that. I'm going to skip in the quadratic formula. You can go to review it, look up online how to do it. Because x should equal to 1 or x equals to 7 over 3. So that means at x equals to 1 and x equals to 7 over 3, here is our critical point. We got 2. So now we need to know, these two critical points, are they maximum or minimum? We use the same method. We plug in x equals to 1 into the second derivative. We have a 6 times 1 minus 10. All right, that gives me -4. So that means it's concave down. If it's concave down, it looks like an N. That means this is going to be our maximum point. All right, now we plug in the second point. So now plug in x equals to 7 to the third to the second derivative. I have 6 times 7 third minus 10. I have 14.2 over 3 minus 10. Now let's do a very quick review how to do a fraction operation. First, we need to find the common denominator. I have 14.2 over 3 minus 13 over 3. Because the common denominator will be 3, so that means I need to multiply 3 over 3 to 10, so that I got 13 over 3. So totally I have 12 over 3, which is equal to 4, is greater than 0. That means this is going to be a concave up. If it's concave up, that means this is going to be our minimum. Now, we still need to find those points. We only know the x value, we still need to know the y value. So to find the y value, we need to plug in x equals to 1 into the original function. We have 1 minus 1 squared and then 1 minus 3. So that gives you 0. That's our first critical point, is 1, 0. In fact, we just found that is our maximum. Remember that finding maximum or minimum, these will be a point. So our maximum value is equal to 0. Now, let's find our minimum. So I have 7, 3 minus 1 squared times 7, 3 minus 3. Simplify it, I have a -13.2 over 27. So the point at 7, 3, -13.2 over 27 is going to be our minimum. So our minimum is equal to -13.2 over 27. Okay, so that should be the solve of these questions. And let me look at the assignment. So the assignment says that you still need to do number 7. I'm going to link number 7 to yourself. Okay, so next one I would like to go over is number 9. So in number 9, again, it's the same. It's find all the critical points and the global extremes of each function on the given interval. Number 9, fx equals to x squared minus 6x plus 5 on the entire real number 9. So this is easy. So that means x can be anything. Again, same idea. We find the first derivative to find all the critical points. So critical point could be maximum or minimum. We don't know. We need to use the second derivative to test that. So here's the first derivative. And then let the first derivative equals to 0. Then we have 2x minus 6 equals to 0. Then we solve it, x equals to 3. Next is second derivative. Second derivative, we have 2. So it's always greater than 0. If it's greater than 0, this is going to be a concave up. If it's concave up, that means we're expecting a minimum. Now, we still need to find what's our minimum. To find it, we need to plug in x equal to 3 into the original function. I have a 3 squared minus 6 times 3 plus 5, I got 9 minus 18 plus 5, which is -4. So that means the critical point is 3 and -4. The minimum value of the function is -4. Okay, next question. We also have a 12, 14, and a 15. Okay, so I am going to do number 12. Number 12, I got fx equals to x minus e to the x. Again, this is on the entire real number 9. First derivative. Well, this guy is easy because e to the x derivative is equals to e to the x. Now, we still need to do the second derivative, then we can find the critical point. The second derivative is when you're taking 1 to the derivative, it's equal to 0, so we don't need to do anything, and then minus e to the x. So that means it's equal to negative e to the x. Okay, now critical point. We want to let the first derivative equals to 0. In that case, I have a 1 minus e to the x equals to 0. Okay, how do I solve for x? So here I have a 1 equals to e to the x. If you take calculus, pre-calculus before, we know that we need to use a logarithm function to convert that into a logarithm function. So to convert that is the base remain the same, which is log base e, and input become output, output become input. We swap the order. This gives you log e, base e of 1 equals x. Or you can think about in another way. E to some number equals 1, that means the exponent has to be equal to 0, because we know that a to the 0 equals 1, 10 to the 0 power also equals to 1, 11 to the 0 power also equals to 1, 984 to the 0 power also equals to 1. All of the numbers to the 0 power is equal to 1, so that we can also solve for x. If you can see that right away, use the logarithm, convert it to a logarithm function. So now we solve that x is equal to 0. Because u to the 0 equals to 1, we have e to the x equals to 1. That tells you that x equals to 0. All right, now we know that at x equals to 0, we have the critical point. Now we need to test out if this is concave up or concave down by plugging into the second derivative. So we have a negative e to the 0, which gives you a negative 1. All right, so that means this is going to be a concave down. Concave down means we have our maximum. We're expecting a maximum. So f of 0 is equal to 0 minus e to the 0, which is negative 1. That means at point 0, negative 1 is our maximum. And since this is not an closed interval, there is no global minimum, because the function can go as far as they want. Okay, let's go over another one with a specific interval. Let's do either 14 or 15. Okay, I'll show you number 14 so that you can do number 15 by yourself. Number 14, I have 2 minus s cubed, and we only discussed that on a certain interval. In our case, would be from -2 to 1. So the step is the same. Find the first derivative. I have 0 minus 3x squared, which is -3x squared. And then second derivative is equal to -6x. Okay, then we need to find the critical point at first derivative by setting the first derivative equals to 0. So when we solve that, -3x squared equals to 0, then x equals to 0 is our critical point. We are expecting a critical point in here. Now, the next thing is we need to substitute the critical point into our second derivative. We have a -6 times 0 equals 0. Oh, we never see that before. This is either greater than 0 or less than 0. So we don't know if this is concave up, concave down. In fact, when the second derivative equals to 0 means what? This is an inflection point. What is inflection point? Does anyone remember? Is the concavity is going to change at that point. Maybe from concave down become concave up, or from concave up become concave down. So that means we don't know if this is a maximum or minimum. But since this is a defined interval, that means we can plug in the critical points to check it if this is a global maximum or global minimum. So let's plug in fx equals to, x equals to 0 into the original function. I have a 2 minus 0 to the third. That gives me a 0. Okay, so that means when, equals to 2. Sorry about that. So that means when x equals to 0, y equals to 2. Now, the other point we need to check is the two endpoint, -2 and 1, because this could be your minimum or maximum. Now, let's check it out. So, f of -2 equals to 2 minus -2 to the third, which is -8. That gives you 6. Oh, sorry, positive 6. Because you're subtracting a negative number, will give you a... Oh, this is equal to 10. You're subtracting a negative number is equivalent to adding that number. So this is equal to 10. So I have -2 and 10. And another critical point, which is the other endpoint, is 1. So I have a 2 minus 1 to the third gives you 1. So that means it's 1, 1. All right, now look at the y value. When we're talking about maximum, minimum, is we're looking at y. We have a 2, -10, and 1. And we know that this is a critical point, but it's either minimum or maximum. In fact, it's an inflection point, so that means also a critical point. But in here, we have value equals to 10. So that means this is our global maximum. This is our global minimum, because it's smallest value. Okay, so that's number 14. I'm going to leave you to do number 15 by yourself. Okay, next question is 17 and 19. So 17 is suppose that we know that suppose f1 equals to 5, f prime of 1 equals to 0. What can we conclude about the point 1, 5? There are a couple options here. A, if f prime of x less than 0 for x less than 1 and f prime of x greater than 0 for x greater than 1. Well, what do we know about that? Look, we know that they have a point f1, the point 1, 5. And then we also know that this first derivative at x equals to 1 is equal to 0. The information that we're getting is this is a critical point. But we don't know if this is a maximum or minimum. We just know this is critical point. And then if x, the first derivative less than 0 for all x less than 1. So that means if here is the graph, when x equals to 1, y equals to 5, we have this point. This is one of the points on the graph. And then when x less than 1, so that means on the left side of the point, all the derivative is less than 0. That means this is going to be going down, because less than 0 means the slope is going to be negative. The slope is negative. That means, oh, sorry, I draw this wrong. The slope is going to be negative, means this is going to be going down. So it must from the top to the down. And then for all x greater than 1, so that means on the right side of the graph, because all greater than 1 is on the right side, less than 1 is on the left side. And then this is going to be greater than 0. That means this is going to be an increasing point. So the point is going to, the graph is to be look like this one. So that means we are going to have a what? A local minimum. It's a parabola. Okay, what about the situation B? Situation B says that f prime of x less than 1 for all the x less than 1, f prime of x, they both less than 1. And then for all the x greater than 1. Okay, this one is going to be interesting. Again, we have a graph, negative infinity to infinity. This is our y-axis, and here's the point 1, 5. This is 1, 2, 0. So for all the x less than 1, we have f prime, which is the slope on the left side of the point, is going to be negative. That means it's going to be going down. And then on the right side, which is when x all greater than 1, the derivative also less than 0. That means also going down. Maybe look like this. So all we know, this is going down. So what do we know about this graph? We only know that this is going to be a decreasing graph, right? And what else? Well, at here, we know that f prime of x equals to 0, so this is going to be a critical point. But by the graph that we're drawing, this is a neither maximum or minimum. But also, this has to be a critical point. That means what? That only left me one option. This is going to be an inflection point. Could be inflection from concave up, become concave down, or the other way, from concave down, become concave up. We don't know yet, but at least we know that this is going to be an inflection point at 1, 5, and also the graph is decreasing. That's all we know. Okay, C tells us that f prime of x greater than 0 for all x less than 1, and f prime of x is less than 0 for x greater than 1. Again, we can draw the graph. Here's the point. And then f prime of x greater than 0, that means this is going to be going up. And then after that critical point, on the right side of that point, the graph is going down. So that means this is going to be a local maximum. D stays f prime of x greater than 0 for x less than 1, and f prime of x greater than 0 for all x greater than 1. So this is similar to the inflection point. So please prove that by yourself. And this is going to be a increasing graph. The function is going to be increasing on the interval. Okay, now next one. Okay, number 19 is defined x is the slope of the line, the blue line, and then through the point 0, 0 and x and fx based on the graph shown. So that means xx will change based on where the black dot is. For example, if the black dot is here, so our blue line is going to look like, I'm going to use a green one. Look like here, you always go through the point 0, 0, and it will change like this ruler. I'm going to show you through the ruler. So the point will move along the graph like that. Does it make sense? Okay, in order to find the slope, the smallest slope, as you can see, with the ruler, we can use the help of the ruler. Look, the slope in here, all the ruler just tell you is 20 degrees, and this one is 13 degrees. So which one do you think have a smaller slope? It's going to be the further lowest point, the local minimum point. So now I have a minimum in here, minimum 1, local minimum 2, and this is our maximum. So the local minimum point is smaller than the local minimum point 2. This in fact is our global minimum. And minimum 2 is one of our local minimum. We have a 2 local minimum and 1 global minimum. I thought this one is lower, but not necessarily means the slope is going to be lower. As you can see the line in here, if I join a 2 line, one is the green one, crossing that point. Let me erase that. So, and then if I have a second line, let's use a yellow pen connecting through the local minimum 2. I got this slope. As you can tell, the yellow line gives you a smaller slope. So that means the minimum slope occur at this point. So A is ask you at what value of x is the slope minimum. So it should be the yellow point, which is from the graph is approximately 7, 8, between 8 and 7. So you can say 8.7 or 8, either way works. No, it's not 8.2, it's more close to 8, but not really 8. It's our local minimum. And then now we need to find our local maximum for that slope. I'm going to delete the blue pen. I can use the blue to find our local maximum. Again, we use a ruler. When the ruler is the tallest, well, you might think it's the maximum, But if I draw a line connecting the maximum point with it, oops. Oh, I shouldn't use a... So as you can see, if I have a slope connecting with the maximum point on the graph, it gives you that slope. Well, it's big, but apparently we can something even bigger is at the beginning of the graph. Well, you see that here is 45 degrees, but here the slope gives you to what? 66 degrees, which is the beginning of the whole graph. So this is a bigger value. So which means at this point, which is about x at when I compare to the original graph, this is 2. So that means b at x equals to 2, xx, the slope which is maximum. Okay, that's number 19. And now let's take a look what other question that we should go over with. Number 22, 23, and 24. So number 22, 23, and 24, the similar question. I'm going to talk about 2 out of 3, so you can do the rest, the other one. So number 22. A function of value x so that f prime of x equals to 0 is given. Use the second derivative to test determine whether each point is local minimum and local maximum. Well, actually I feel like I just need to do one and then you can do the rest of the 2. So for local minimum and local maximum, if they given you the point, the critical point, if the first derivative is positive, that means the graph is going to be concave up. It looks like a bowl or a U. Oh, sorry. So the graph is look like this way. So you will have a local minimum. But if your second derivative is less than 0 at that point, it's going to be a concave up, a concave down. It looks like an N, so you will have a local maximum. Now, number 22. We are given a function fx equals to 2x cubed minus 15x plus 6. S equals to 0 and 5 is your critical point. Now let's find the first derivative. We have 6x squared minus 13x plus 0. And then the second derivative is equals to 12x minus 30. Yes. Did I copy the question right? Alright, and now we need to plug in the point x equals to 0 and 5 into the second derivative. So, second derivative and x equals to 0, we have a 12 times 0 minus 13 equals to negative 13. So this is less than 0. And then f of 5, we have 12 times 5 minus 13, which is equal to 13 greater than 0. So that means less than 0 is concave down. We have our maximum at x equals to 5, and then we also have our minimum at x equals to 5. Oh no, this is x equals to 0. Sorry. And I still want you to find what's the minimum, what's the maximum. So we plug in the number into the original function to find the minimum and maximum. So I have a 0 minus 0 plus 6 equals to 6. So that means the maximum equals to 6, and then f of 5, I have 2 times 5 to the cube minus 15 times 5 squared plus 6 equals to, let me calculate that with my calculator, negative 119. So our local minimum is equals to negative 119 at x equals to 5. Here is at s equals to 0. Okay, that's number 22, and it's your turn to do number 23 and number 24.